Good morning to all of you. So, last class we were discussing this line shapes, how it is affected when you have uh, asymmetric. The electronic environment is asymmetric. The interaction of electrons is different in different directions. Then this kind of thing arises. You have the line shape will be changing from a symmetric. So this is a symmetric absorption profile where just a rise and fall you can see. So and the derivative is like this, a typical one. So this is what typically is observed, and other things are represent that is given is the representation when the situation is not isotropic. Then in one direction, along the direction of applied field along z-axis, if you have somehow it turns out that the electrons are more uh, 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 affected along z direction. In that case they will be greater, it will be much easier to bring them into resonance, and so they will appear. So this you see small peak for the GZ appearing first in the, if you are scanning from the magnetic small magnetic field to high magnetic field side, it will appear first. So this is the applied magnetic field, and the z along z direction you are having this thing that appears. Then you scan it further and you get another peak that is for x plus y along both the directions. So g value is represented over here. First derivative tells you about this. So like this, you can, the reverse situation will be that gz is smaller, and in that case, so this is the prolet oblet kind of thing that we have discussed earlier. So along z direction, now because it is less, the g value is less, so you will have to make more effort to bring into in resonance. The magnetic field at which resonance will occur will be higher, so this will appear here at a larger b value. Okay, smaller g, so simple correlation you are getting, because why it is happening like h mu, which is equal to g into this Bohr magneton. uh, Somewhere I had written is beta, or you can write it as mu v Bohr magneton, that's better, and then the v resonance. So this magnetic field required for resonance, so it's quite clear. If g is high, you can reach the, if h mu is fixed, you have a microwave frequency which is fixed, then b resonance that we are talking about will be h mu by g mu v. So Bohr magneton is constant. You need to have, so if you know the microwave frequency which is fixed, then higher the value of g, the magnetic field value will be less. So the first thing you can see in the uh, when this part is there, axial with gz is greater, then because gz is higher, the magnetic field required for the resonance is less. In this second case, in the second axial case, where it is the prolet oblet electronic environment, electron density, looks like, in that case V resonance would, for the same particular along z direction, to bring it into resonance, because it is now less than as compared along z direction, the magnetic field required will be higher, right? So that's why you are getting the signal at a higher value of magnetic field, and x and y both are equal. So whenever you apply, change the if the orientation of the molecule changes along x, along y, both add up to give you a larger signal on this part. In both cases you are getting larger signal for in terms of absorption, in terms of signal intensity, you are getting larger signal for x and y because they are too much greater in number. They are twice in number as compared to the z1 single. So all such absorptions, so this is a line shape that is changing, and this is what I wanted you to note, take note of it. Okay, what else did you note? You also noted that one more thing that was important is that you should not, so in such cases where such happens that the peaks are overlapping with each other, one peak is here and another peak starts coming over here, so overlapping, net result is that what you are getting like this, resultant is what you actually observe. So remember, this is, so in such cases you have a rising portion and then there is no fall, falling part is not there, so you do not get a negative, this kind of peak is not obtained, right? And overall result is that here you have a situation where the slope is almost zero, absorption is finite, much higher, very close to the first peak value, but it is the change in absorption with respect to change in magnetic field is nil, it is zero, and so this appears zero. So you should not, when you looking at the derivative spectrum, you should not conclude by simply looking in this manner that there is no absorption at this particular point. There is a finite absorption. Okay, if you are getting this kind of profile, then you can definitely say that okay, here the peak, this kind of profile, yeah, this one, first one. So if this is a peak, you will get zero slope, so slope will be zero here, and also zero value will be obtained here. There is no absorption, there is no absorption, so because the absorption is zero, you have 0 here, 0 here, but here because the change in absorption is 0, the slope, so that's why you are getting 0 value here. So similar situation, see the situation here arises is that change in absorption is 0, but the absorption is finite, it is not 0. So these are finite points with which we can move ahead, and the rhombic one is the case where magnetic moments along x, y, z are not, all are different. Okay, so in such cases you can get spectrum like this, and first derivative spectrum will look like this, g, z, g, y, g, x. Okay, so now we can move ahead, and this is what, so we have, if we are looking at a complex like this which has 4 ligands in xy plane of one type and 2 ligands of another type along z axis, then if they are powdered and kept in the, if we kept for EPR spectroscopy, you will find, so this is how we add up the electron in free state, electron in such environment. So that is a specific, so G value has an additional factor of Gz, which incorporates both the things. What are the two things? The spin orbit coupling constant and the del E, the separation between the energy levels, the lowest unoccupied energy level next to it. Similarly, you can think of this thing, so all those factors count here, and this you get a two spectra, two peaks, sorry, like this. Then we discussed that to understand it better you have to take a note of the how the B is oriented with respect to the molecular axis. So theta and phi were, we found its projection of the magnetic moment of the molecule in the xy plane. So you can get three components like cos cos theta, sin theta, and sin theta cos phi. So this is finally the equation, and you can possibly plot it versus the magnetic field, how it varies with the angle theta, and the magnetic field required to bring into resonance. This is the magnetic field that is required to bring this sample into resonance. The absorption will occur at that point and a peak will be obtained. So applying that polar coordinate thing, expanding this form of the G, we get this kind of thing, which further simplifies into this. And I told you that look at this graph. So you have angle theta versus B, G value versus B, the magnetic field applied, and you can see that the G varies as a straight line like this. You can also see that for the that there is a straight line behavior in this portion, in the middle portion. So the angular dependence has with the change in angles, you have a regular variation in G. But if you are looking at the angular variation, so the angle and the B resonance, so magnetic field required for resonance, so it is insensitive in this portion, in the when the theta approaches 0 or theta uh, approaching pi by 2. In these two cases, the magnetic field required is remains. You can see that this line rises like this, and so there is no change in magnetic field. The angle theta keeps on changing in this region, so there is no effect on the magnetic field value required for resonance, and even though the angle changes very sharply. Okay, so this is at two ends. You can see clearly this is happening. So angular dependence of axial G values. So this is how we understand. Okay, so the calculated values are like G perpendicular is 2.05, G parallel 2.4, and this is for this copper 2 site, which yeah, we can. So uh, so the G values keep. So what we have found that G values can be easily determined from the EPR spectrum. If you are observing the EPR spectrum, all these components, the G parallel, G perpendicular, can be easily determined if you are able to locate the position of the points. Uh, so okay, uh, so from the absorption type spectrum, we have first derivative. So we usually we have seen that absorption spectrum, which normally could have been obtained, is not the what usually you get on the screen while doing EPR spectrum. It is the first derivative instead of the absorption. G values can be easily recognized from that. Uh, so this magnetic field, keeping the frequency fixed, you can vary the magnetic field, external magnetic field V naught, and keeping the frequency fixed at 100 kilohertz, the spectrometer can be done. The spectrum can be recorded, and this is the derivative signal that we were talking about. So we have seen that derivative spectrum EPR of species of different types, S is equal to half systems. So we can there's three different component possible maximum if for one set of things, uh, uh, and yeah, if there is symmetry some sort of, then you can have two values, perpendicular and parallel. And then if it is very spherically symmetric environment, isotropic, then only one value of G will be obtained. So it is the resonance, the field B resonance that we talked about, the field required for resonance, magnetic field, is not the fingerprint of the molecule, but the G factor is. G factor, if you are able to determine, that is taken as a signature of a particular species present, and this is what we try to determine when in EPR spectroscopy. So what we have seen earlier, I told you through the graphs also, that something that is having a high G value will appear at low magnetic field and vice versa. So we saw that when G along Z axis is high, that appeared as a small peak at the lower magnetic field side. Okay, so that was, so based on that, this is the what, so X band spectrometers are the most widely used one. X band is here in this table. Yeah, so all the fine things, 9.5 gigahertz V resonance, and this was the thing that we discussed earlier. So how the line shape changes depending on the environment in which the electron is put, the unpaired electron is. Okay, so the derivative spectroscopy that is done has some advantages as well as some disadvantages. So one of the advantages is that any drift in the magnetic field that can be taken care of rapidly. uh, so it helps in enhancing the resolution, because if imagine the line shape that you are having, you may get confused that it is one peak or two. Sometimes this one is not so good and it only show a rising portion like this, then you might get confused. But if you draw a first derivative curve, then if you are getting two clear, one clear peak over here and another like this, then you are sure that there are two components present. So the derivative spectroscopy is somehow helpful in enhancing the resolution. If you have too many signals congested in a very small range, then derivative spectroscopy really helps you out. Uh, so we have already discussed a slowly changing part of the spectrum. I already told you through that part where you have near zero slope and no and should not be interpreted as a no intensity one, because we saw that there was finite intensity here. So this is the point that is made out over there. This portion is where you are getting 0. So that was, it is wrong to conclude that there is no intensity over there. Okay, so although in derivative display you will get something like that, so that was problem sometimes that you might get confused, but because original absorption spectrum is not available directly, you are getting this derivative spectrum. So we have seen in previous slides what that kind of thing, the clearly shows. So flat region between G parallel and G perpendicular, that corresponding to finite absorption. So sometimes, so this is a difficulty when we are talking about the pros and cons. The disadvantages is that sometimes it is difficult to estimate the concentration of EPR samples, since a large part of the signal appears to be hidden in that G, between the G parallel and G perpendicular. And another thing is that you should never assign a large intensity to an isotropic signal, because in case of anisotropy, the same signal is divided into, it is spread over a wide magnetic field range. So you have to take the sum of all those intensities, and that may be higher than this thing. So what I'm talking about is that the signal sometimes not here. Where is that? The signal, next slide, I think it will be there. So now the hyperfine structure is also clear. If it is in case of, so very good scheme you can see here. So when there is no interaction, first part, you get clean, this kind of one peak and a valley. Peak and the valley is the feature of an isolated an electron which is not having anisotropic environment, anisotropic interactions. So when you have interaction with a nucleus which is nearby, having I is equal to half as the nucleus spin, it splits into two. Now see, the signal intensity was higher and the same signal has split into two, so now the intensity will be intensity of each of them will be same, will be equal, and it will be such that when you add the two you get this overall. Now if you are having nucleus spin as I is equal to 1 nucleus with I is equal to 1, the same signal is splitting into 3, and see now the intensity that we are showing is even less. So it is the same overall intensity that is now divided into 3. That's why it is looking less. But yeah, you should know that it is the same, coming from the same electron, and because of the interaction with the nucleus it has split into 3. So all these intensities correspond to one thing. So similarly, as this happens, if the spin is I is 3 by 2, again it splits into 4. Look at the intensity. What I am highlighting is, look at the intensity pattern of how it changes. It splits into 4 signals, and the sum of these 4 signal intensity should be equal to the original one. Sum of the 4 intensities, so sum of the intensity should be equal to what? This one. So same thing you can think of when you are having with interaction with one nucleus of I is equal to 1, or one when it splits into 2 or 3. So individual signals of this 3 or 2, the splitted pattern should be equal to the unsplitted pattern which is having no interaction with any of the nucleus. So that was one situation that we discussed. Now you can, so now segment B of the picture shows you when there are two nuclei with I is equal to half. So you know the pattern, Pascal triangle, 1 1, and each of them splits into 2. So you have 1 is to 2 is to 1. You can see the signal intensity, 1 is to 2 is to 1. You are getting that? So 1 2 1. So relative ratio of the intensities is like this. Then 3 of half Newton, so here 1 is to 3 is to 1, so 1 3 3 1, and then 4 nuclei of I is equal to 1 types. So you can go on in increasing the number of nuclei, and you can get number of splittings that will be observed. and what will be the intensity, that also you can predict. And now you know that it is the same initial intensity in absence of other nucleus, that is divided into 3 or 4. So you, if you are drawing to the scale, the sum of this should be equal to the original one. So part C shows the how spectrum looks of a species that has interaction with 4 nuclei of I is equal to 1 type in the so all these nuclei that we have talked about are all identical whenever it is interacting with 3 nuclei of one type, 2 nuclei of one type, or like that. So if the nuclei, one nucleus is of half, another nucleus is in 3 by 2 or 1, then the pattern looks very complicated. We have not yet gone into that. But in few examples I told you, yeah, initial example how the hyperfine structure will be built up. There you have to take the first this one which is having higher hyperfine constant, and then you start do the other. The order will not matter much, but it becomes convenient that you start with the highest possible value if there are more than uh, one type of nuclei present. So you also see here the dotted, look at the dotted line. Always this dotted line is the center of the things lies over here. You can also see that when you are having splitting into two, it is passing through a point where that central line is passing through a 0, 0, 0, 0 in all these cases. Okay, so okay, so next we are taking some interesting examples of the complexes that can be thought of. So copper perchlorate, Cu2 plus in CuClO4. So this is the spectrum, EPR spectrum of CuCl4. So you are getting two signals, two set of signals, one for G parallel and G perpendicular. The G parallel one is clearly splitted into 1, 2, 3, 4. So 4 peaks can be seen for the G splitting, and this is due to 63 copper 65, both have a nuclear spin of 3 by 2, and because of that the lines got split into 4. Okay, because there are 4 orientation of the nucleus, nuclear angular momentum that is possible, corresponding to the 4 mi values. Okay, so that's why it is splitting into 4, and the magnetic moments can be two isotopes similar, so you obtain, so they both the signals due to the interactions both coincide, whether it is from 63 copper or 65 copper, both appear at the same place. They have 3 by same spin, so the interaction is not much different in spectroscopic terms. They appear at the same position, whether the electron interacts with copper 63 or copper 65. Okay, so the hyperfine splitting that we are seeing, uh, so the anisotropic behavior is clearly seen in the graph, better resolved in one direction, that is the G parallel direction, which is contains the molecular axis as compared to other two directions. Hyperfine coupling for G parallel for C2 plus is greater, that's what we can see, and so we clearly a splitting pattern is observed. You can see this, and the large splitting of G parallel is line, and in G in case of G perpendicular there is hyperfine interaction is there, but it is too small to be observed on the spectrum. So this is some typically happening in this case that you can see. Okay, so perpendicular, we are not able to observe the uh, splitting pattern, hyperfine splitting, possibly because the interaction, this spin, or this interaction, the splitting constant, the hyperfine splitting constant is very small, and that's why we are not able to observe it. In case of G parallel, it is significant and splitting can be observed. So it is an example of D9 system. Another D9 system is nickel plus, nickel 1. So nickel 2 plus is D8, nickel 1 plus is D9. So this is an example of D9 system again, uh, which is similar to copper 2 plus. So this is an enzyme, reductase enzyme, that appears in some bacteria, methanothermobacter, in the reduced form. So there are two spectrum that has been shown with the growing cells in nickel isotopes, in natural nickel isotopes occurring natural. Okay, and the second one shows that in not the natural isotopes, only the one of the isotopes has been taken, 61 Ni, for the growing cells. So clearly we can clearly see that in the first one, the top spectrum, there's something you can see this side, which is small peaks are there, not very well resolved. Similarly, you can see a clear part over here. So again, the case of the structure is given in this side. So you can see the ring, like the it is like it is a macrocyclic ligand which is encircling the nickel. Chelate ring is formed in. So methyl, what we observe here, there is a tetrapyrrole ring that in the structure we have just seen, which was coordinating with the nickel. And what we see here is, in this particular case, not, now you see the structure here, nickel n n. So not nitrogen is magnetically active, N14 is magnetically active. It has this I value of 1 quantum number. So each the interaction of the electron on nickel interacts with nitrogen nuclei, and that gives some splitting pattern. So that is called hyperfine interaction. Why it is called super hyperfine? Hyperfine interaction is something that one, if the electron interacts with the nucleus of the same atom, like here the electron is on nucleus, sorry, Ni nickel 1 plus, but it is interacting with the nucleus of uh, neighboring atom, not the nucleus of nickel. So that is a super hyperfine interaction. Hyperfine interaction, if that electron would have interacted with nickel nucleus, that would have been hyperfine interaction. And if it is interacting with some nearby nucleus, then that is super hyperfine interaction. So this particular case we see in nickel is that of hyperfine, super hyperfine interactions happening. And up in the top panel you see the spectrum. You are getting very fine structures for these values, perpendicular. Okay, so super hyperfine lines, that so two spectrum that we have seen here. So super hyperfine lines we observed, and the 4 nitrogen ligands can in the G perpendicular peak. So this was the perpendicular G perpendicular. G parallel. G parallel is not much resolved, but still you can see something is there. 1 2 3. Still you can detect, but you are not very sure that these peaks are due to the interactions. So to resolve that peak, what was done? Enriched with, if you enrich instead of natural abundance, you enriched it with 81 Ni. So 81 Ni is magnetically active, and then, so if that is done, it has a spin of 3/2, and so you can expect it to split into 4. Yeah, enzyme when enriched with Ni61, it splits into the spectrum which is shown in the lower panel. Okay, resulting spectrum. So in addition to the hyperfine structure, now you can see the hyperfine structure due to the nickel isotope. So G parallel is now split into 4 lines very clearly, you can see. So the splitting, so something that was not very well resolved, when the isotope is enriched, you are having more of that magnetically active isotope. Then it is very refined one, you can see how it is split, clearly seen. So splitting on the G perpendicular peak is only seen as a broadening here, and the lines, since the, so because the hyperfine splitting is less than the line width of the peak, so that's what we observe here, G perpendicular thing, where you can only see kind of broadening happening. So this is similar to what we observed with copper. Both are D9 systems, and that's how it comes out. Okay, so we have almost completed this part. So another example, if I take for understanding this inorganic structure present in biological systems, is that of chloroperoxidase, which contains the vanadium V4 plus, vanadium in +4 oxidation state, which is a D1 system. And this is the spectrum that looks like, the EPR spectrum looks like this. So you can see that G parallel, G perpendicular, both are appearing almost at the same place, at the same place. Okay, sorry. So just a few minutes. Okay, so vanadium 4 plus. So this is present in enzyme form, in the enzyme peroxidase, and the peculiar signal you can see here. Although differential interactions are there, G parallel, G perpendicular, the splitting that you see between the lines here and the lines in G perpendicular case are different. Okay, although they appear at the same place, and so it's a very looks like a complicated spectrum, but it is easy to see that some of the lines you can see were typically observed for G perpendicular like this. So each of the line is split into 1 2 3 4 5 6 7 8 8 lines, 8 things. So this is, vanadium has axial symmetry. Its powder spectrum consists of one. So see, the G perpendicular is having 1.95, G parallel is 1.9, very close to each other, and that's why we are having this situation. complicated situation that arises, because both the G values are only separated by 0.03 value of only second decimal place. So vanadium has nuclei which is 51, I is equal to 7 by 2. So of course you can expect by simple ball stick model 2i plus 1 signals lines, it will split into these, and so that happens. And because the two are the original signal is positioned very close to each other, 1.95, 1.98, so it is there is a strong overlapping that happens, and not so it is difficult to observe all lines very clearly, but you can still try doing that, and you can resolve these hyperfine couplings. So coupling constant for in one direction is very strong, coupling constant is very high. Coupling is strong in one case, in the hyperfine coupling in another case is small, and so it masks. You can see the masking of uh, G parallel signal due to the G perpendicular because of that. So this is also termed overshoot in this spectroscopic sense. So hyperfine lines of G perpendicular it passes through the G parallel peaks. So from one side to the other, it goes from this end to this end, cutting through the G parallel peak. G parallel peak के आर पार उधर चला गया. The lines of G perpendicular have different orientation, uh, and G perpendicular, of course, both have observed in different orientations. Uh, so these hyperfine lines are also observed in different orientations. Yeah, you can see that in this one. Sorry, these are no. This one is due to this. Okay, so we'll okay. So this is the discussion about the line shapes and splitting patterns. And the last part would be Kramer's system, spin multiplicity and Kramer's system. So that we will be able to finish by tomorrow. We will be finishing the EPR part. So this week we have finished, we will be able to finish both. The NMR EPR will be done. And next week we will start with photoelectrons spectroscopy.